In November of 2024, a team of scientists published a paper that quietly rewrote something astronomers had accepted as fact for almost 40 years. The data behind it wasn't new. It hadn't been collected by any modern instrument, hadn't come from James Webb or any spacecraft currently in operation. It came from a single, brief flyby conducted by a probe launched in 1977, using instruments built with 1970s technology, data that had been sitting in archives since 1986, waiting for someone to look at it differently. When they finally did, it overturned nearly 4 decades of assumptions about an entire planet and reopened a question about alien oceans that scientists thought had been closed for good. This is the story of what Voyager 2, still transmitting from beyond the edge of our solar system 49 years after launch, has quietly forced us to reconsider. To understand how a single old dataset could do that, you have to go back to what Voyager 2 actually was, and still is. Launched on August 20th, 1977, just weeks before its twin, Voyager 1, the spacecraft was built to take advantage of a planetary alignment that happens roughly once every 176 years, letting a single probe use the gravity of each outer planet to slingshot toward the next one. Picture it leaving Earth, carrying a golden phonograph record bolted to its side, engraved with sounds and images meant to explain human civilization to whoever or whatever might eventually find it drifting between the stars. A message its own builders knew might outlast the spacecraft, the sun, and possibly our entire species. Voyager 2 became the only spacecraft in history to fly past all 4 giant planets in our solar system. Jupiter in 1979, Saturn in 1981, and then, in a feat no mission has repeated since, Uranus in 1986 and Neptune in 1989, discovering 11 new moons and 2 new rings around Uranus alone, and capturing the first close-up images of a massive swirling storm on Neptune that scientists nicknamed the Great Dark Spot. After Neptune, its main planetary mission complete, Voyager 2 kept going, arsing downward out of the plane the planets orbit in, on a trajectory that would eventually carry it out of the solar system entirely. In November 2018, it crossed the Heliopause, the boundary where the sun's own bubble of solar wind gives way to true interstellar space, becoming only the second human-made object, after Voyager 1, to leave the solar system altogether. It has been transmitting from interstellar space ever since, using a radio signal so faint by the time it reaches Earth that receiving it requires some of the largest antenna dishes ever built, pointed at a precise, calculated spot in the sky where a spacecraft, smaller than a school bus, is still somehow calling home. But the discovery that just rewrote 40 years of textbooks didn't come from way out there in interstellar space. It came from that brief flyby of Uranus back in January of 1986, and to understand why it mattered, you first need to understand just how strange that flyby made Uranus look. When Voyager 2 swept past Uranus, its instruments recorded something that didn't match any other planet in the solar system. Picture the planet the way mission scientists eventually had to redraw it. A pale blue-green sphere tipped almost completely on its side. Its magnetic field wrapped around it, not like a neat, symmetrical bubble, the way Earth's or Jupiter's is, but tilted nearly 60 degrees away from the planet's own spin axis, and already lopsided, chaotic geometry before anything else about it was even factored in. Inside that tilted field, the planet's magnetic field trapped energized particles into a radiation belt so intense it was second only to Jupiter's infamously brutal radiation environment, the kind of field that would shred sensitive electronics on a spacecraft. Radiation belt was made almost entirely of extremely energetic electrons. Almost everywhere else inside Uranus's magnetic field, the space was strangely, eerily empty, nearly devoid of the other charged particles that planets normally collect, from the solar wind and from moons orbiting inside their magnetic bubble. It was as if Uranus had 2 personalities stitched together, one region packed with dangerously energetic radiation, and everywhere else an almost total vacuum. Nothing about it matched Jupiter, Saturn, or Neptune. For nearly 40 years, that mismatch became one of the defining facts of Uranus itself. Scientists wrote the planet into the record as a genuine oddball of the solar system, its bizarre magnetic environment treated as a fundamental, permanent feature of what Uranus simply is. That label came with real consequences, and this is where the story connects to one of the biggest open questions in planetary science. Which moons in our solar system might be hiding oceans? 2 of Uranus's moons, Titania and Oberon, have icy outer layers similar in some ways to Jupiter's moon Europa, which scientists confirmed has a vast subsurface ocean by studying subtle variations in its own magnetic environment. Here's how that technique actually works. In plain terms, a moon orbiting inside a planet's magnetic field is constantly bathed in a field that shifts and rotates as the moon moves through it. If that moon has a layer of salty liquid water hiding beneath its icy surface, that liquid conducts electricity, And the changing magnetic field passing through it induces a secondary magnetic field of the moon's own, a faint magnetic echo generated purely by electricity flowing through hidden saltwater, detectable by a passing spacecraft's magnetometer, even though the ocean itself stays completely hidden under miles of ice. It's the same basic principle used to find buried electrical conductors here on Earth, just applied across hundreds of millions of miles of empty space. That technique is exactly how scientists first confirmed Europa's ocean, by watching how the moon distorted Jupiter's own magnetic field as it orbited. When researchers tried applying that same detection method to Uranus's moons, using the magnetic field Voyager 2 had recorded back in 1986, they found nothing. No induced signal, no evidence of a hidden ocean, no reason to think Titania or Oberon were anything other than solid, unremarkable ice. For most of the last 4 decades, that was treated as a settled, if disappointing, answer. Here's where the new analysis changes everything, and it hinges on a detail that had been sitting quietly in the data the entire time, unnoticed for decades. When the research team went back through Voyager 2's own solar wind measurements from the days leading up to its Uranus flyby, they found a steady, unmistakable rise in solar wind pressure in the hours before the spacecraft arrived. Something out there in space had been compressing the solar wind into a denser, more forceful stream just before Voyager 2 made its closest approach. Modeling what that kind of compression would do to a planet's magnetic field produced an almost exact match for the strange, lopsided environment Voyager 2 had recorded. The rare solar wind event had squashed Uranus's entire magnetosphere like a fist closing around a balloon, compressing the energetic electrons into a thickened, intensified radiation belt while squeezing nearly everything else out entirely, the way pressure squeezes juice out of a piece of fruit. According to the researchers' own modeling, that kind of extreme compression only happens to Uranus's magnetic field around 4% of the time. Voyager 2 had exactly one flyby, one brief window lasting only a matter of hours, to ever study this planet up close, and by pure chance, it happened to arrive squarely inside that rare 4%. Run the numbers the other way and the strangeness gets even sharper. Across the entire multi-year approach to Uranus, across every possible day the spacecraft could have made its closest pass, the mission's one and only shot at this planet landed on one of the roughly 1 in 25 windows where the data it collected would end up systematically misleading an entire scientific field for decades. Nobody planned that. Nobody could have. Trajectory planning for a flyby happens years in advance, locked in by orbital mechanics and fuel constraints long before anyone could know what the solar wind would be doing on the actual day of arrival. One of the study's lead authors put it about as plainly as a scientist ever put something on the record. If Voyager 2 had arrived just a few days earlier, before that solar wind jet hit, it would have observed a completely different magnetosphere at Uranus, and an entirely different picture of the planet would have made it into every textbook written since. Once researchers rebuilt what Uranus's magnetic field actually looks like under normal uncompressed conditions, the picture of its moons changed along with it. Scientists had long assumed that Titania and Oberon regularly drift in and out of Uranus's magnetic field as they orbit, spending significant stretches of time completely outside its influence. The corrected model shows that assumption was itself an artifact of the squashed, temporarily shrunken field Voyager 2 happened to observe. Under normal conditions, researchers now believe those two. Moons actually spend the overwhelming majority of their orbits sitting fully inside Uranus's magnetic field, constantly exposed to its variations rather than only occasionally brushing against it. That distinction matters enormously because it's exactly the kind of sustained magnetic exposure that would make the Europa-style ocean detection method actually work if there's a hidden electrically conductive ocean down there to find. The reason scientists found no evidence of oceans on Titania and Oberon wasn't necessarily because there aren't any. It may simply be that Voyager 2 studied those moons under the one set of conditions where the ocean detecting technique itself couldn't have worked properly, even if an ocean was sitting right there beneath the ice the entire time. Sit with that for a second, because it's a genuinely strange kind of discovery. Nobody launched a new mission. No spacecraft got any closer to Uranus than it already had decades ago. The entire finding came from realizing that a single 40-year-old observation had captured an edge case, a rare and temporary weather event in space, and had been quietly mistaken for the norm ever since. It's the scientific equivalent of judging an entire ocean's character from one freak, once-in-a-generation storm, simply because that storm happened to be the only time anyone ever looked. That correction doesn't prove Titania and Oberon have oceans. It's important to be precise about exactly what changed and what didn't. What changed is the confidence with which scientists could previously rule oceans out. The absence of a detected signal in 1986 is no longer meaningful evidence against an ocean because the conditions during that flyby were never capable of revealing one in the first place, even hypothetically. The moons have gone from a settled no back to a genuinely open question. One that current models suggest is now worth serious consideration rather than one that was already closed. Confirming an answer either way will likely require a dedicated future. Mission? Something planetary scientists have already recommended as a priority. A proposed Uranus orbiter and probe. A spacecraft that would spend years actually orbiting the planet and its moons, rather than passing through in a matter of hours, doing exactly the kind of sustained magnetic monitoring that a single 1986 flyby was never built to provide. Voyager 2's crossing into interstellar space wasn't quiet, either. As it pushed through the Heliopause in 2018, its instruments recorded something Voyager 1 hadn't clearly seen 6 years earlier at its own crossing. A distinct, thin magnetic barrier sitting right at the edge, a layer of intensified magnetic field wedged between the heliosphere and true interstellar space, strong enough to noticeably influence which cosmic rays from outside our solar system are allowed to leak in and which get deflected away. It gave researchers their clearest picture yet of the actual physical wall separating the sun's bubble from the galaxy beyond it, a boundary earlier missions had only been able to theorize about from a distance. While all of that was unfolding back on Earth, the spacecraft responsible for the entire Uranus mystery has kept moving, and it hasn't stopped generating new puzzles of its own. As of this year, Voyager 2 sits more than interstellar space, and it is still, remarkably, sending back usable scientific data using several of its original instruments, including its magnetometer and its plasma wave detector. Signals from that far away take more than 20 hours to reach Earth, one way, meaning every single piece of data researchers analyzed today left the spacecraft the better part of a full day earlier. And the interstellar environment it's traveling through has been delivering its own unresolved mysteries in real time. Researchers tracking magnetic field data from Voyager 1 on the opposite side of the solar system from its twin discovered that a major pressure disturbance that struck the spacecraft back in 2020 pushed the surrounding magnetic field to a new elevated strength. And unlike every previous disturbance recorded before it, the field never fully relaxed back down afterward. Years later, it's still sitting at that heightened level, a persistent shift that doesn't match existing models for how the interstellar magnetic environment is supposed to behave after a passing disturbance fades. Researchers modeling the equivalent conditions along Voyager 2's own trajectory have projected that a comparable shock or pressure front could sweep past it around this same general window, meaning that somewhere out past the edge of the solar system, right now, Voyager 2 may be sailing directly into the next version of exactly this kind of unresolved mystery, with scientists back on Earth watching the data arrive in close to real time to see how it behaves. Keeping that signal alive at all has required its own kind of quiet heroism from engineers back on Earth. Voyager 2 runs on a radioisotope thermoelectric generator, a power source that converts the heat from decaying plutonium into electricity. And that power source has been losing a small, steady trickle of output every single year since launch, the way a battery slowly fades even when it's never used. Engineers have spent the better part of the last decade switching off one instrument after another, starting with the most power-hungry, just to keep the remaining ones alive a little longer. In 2023, mission engineers found an additional few years of life hiding in the system by disabling a safety mechanism originally meant to protect the spacecraft's voltage, a calculated risk they judged worth taking specifically so Voyager 2 could keep collecting data through exactly this kind of moment when new interstellar disturbances might be arriving. Today, both Voyagers operate what NASA calls a kind of survival mode, running only a handful of their original 10 science instruments, with engineers openly acknowledging that at some point, probably within the next few years, the power will finally drop below what even one instrument needs to function. And after 49 years, the conversation will finally, quietly end. There's something worth sitting with in the fact that both of these stories, the decades, old Uranus mystery, and the ongoing interstellar puzzle, come from the exact same aging spacecraft. Voyager 2 wasn't designed with modern computer modeling in mind. Its instruments are simpler, by any modern standard, than what flies on almost any spacecraft launched in the last 20 years. And yet it keeps generating discoveries. Anyway, sometimes decades after the data was actually collected, simply because the questions scientists know how to ask and the models they can build to test them keep getting more sophisticated even after the spacecraft itself has moved on to somewhere else entirely. The 1986 Uranus flyby lasted only a matter of hours. The insight buried inside that data took 38 years to surface. That's really the through line connecting everything about this mission. And it's worth stating plainly rather than dressing it up further than the facts already support. Voyager 2 isn't making new discoveries the way a live telescope does, by pointing at something new and reporting back immediately. It's doing something almost stranger. It collected a finite amount of data across a handful of brief planetary encounters in one long continuing journey through interstellar space. That same limited data set keeps yielding new, sometimes genuinely surprising answers, every time someone with a better model and a fresh set of questions goes back and looks again. Nobody expected in 1986 that the Uranus flyby data would still be actively rewriting scientific consensus in 2024. Nobody currently knows exactly what Voyager 2's interstellar data will reveal 5 or 10 years from now, once today's readings have had time to be modeled, checked, and reconsidered by researchers using tools that don't exist yet. So here's where that leaves things. 49 years after a spacecraft the size of a small car left Earth on a mission originally planned to last 5 years, it is still transmitting. It is still, occasionally, still teaching us something none of the scientists who built it could have anticipated. 2 of Uranus's icy moons went from a closed case to an open question because of a single unlucky flyby and a rare 4% chance of bad timing that nobody even knew to suspect until someone looked again. Think about the scale of that for a moment. The engineers who built Voyager 2 designed it using slide rules and hand-drawn schematics, working with less onboard computing power than exists in a modern key fob. They could not have anticipated Nature Astronomy publishing a paper in 2024 built on their spacecraft's brief 40-year-old data. They couldn't have known that a technique for detecting hidden oceans on distant moons, using magnetic induction, wouldn't even exist as a concept for another 2 decades. They simply built the most capable instruments 1970s engineering allowed, pointed them at whatever the spacecraft happened to fly past, and trusted that the data itself, once recorded, would still have something to say, however long it took someone to come back and actually ask it the right question. That trust turned out to be justified almost 40 years later, and there's no reason to assume this is the last time it will be. And somewhere past the edge of everything the sun's own influence can reach, an old, faithful, half-century-old machine keeps sending back numbers, one exhausting radio signal at a time, from a region of space no other human-built object has ever mapped before it. Its power keeps fading, a little more every year, and the day is coming, probably within the next few years, when the last instrument finally goes dark and the signal stops altogether. But whatever it finds between now and then, and whatever it already sent home that nobody has fully understood yet, probably won't be recognized the moment it arrives. Based on everything that's happened so far, it might take another few decades before anyone realizes exactly what it already told us, sitting quietly in an archive somewhere, waiting for the next person with a better model and a better question to go back and look again.